So now I have this question for you. Question says, do we have a set with no members in it? And if they had a set with no members, how do we represent them? The answer to the question is yes, they have sets with no members in them. For example, the set of all numbers that are even and odd at the same time. Do we have a number that is even and odd at the same time? The answer is no. We call this set an empty set. How do we denote that? We usually just write two curly brackets next to each other with no element inside, or we use this symbol. Empty set, empty set. Well, so how do we compare sets? What is the tool to compare sets? So take a look at this example. Example says, what is the relation between following sets? So the first set in part A is a set including 1, 2, 3 elements. B is 3, 1, 2. And C is given as, let me write down C here, we need a little bit more space. 1, 1, 2, 3, 3, 3. Okay, so let us analyze each of them separately, see what's the relation and connection between them. Set A has 1, 2, 3 members. What's the cardinality of set A? The cardinality is 3. How about set B? What are the members of set B? Set B is the set 3, 1, 2, and I can rearrange these elements. I can write 1 first, then 2, then 3. It doesn't make any changes to the set or the collection of elements if I change the order. It's different from an ordered pair. What's the cardinality of set B? Cardinality of set B is also 3. Well, what's the relation between A and B? As you can see, A and B are the same. So we write A is equal to B. Let us take a look at C. Set C has 2 1s. 1 is repeated twice in this set. 1 and 1. I'm going to use just one of these two to represent number 1. So I'm going to write down 1 as the representative of these 2 1s. I have 2 repeated ones. I'm going to write down 2. 3 is repeated 3 times. 3, 3, 3. I can take one of these 3s to represent 3 in this set. So I'm going to forget about set C, the original set C. My set C can be written as 1, 2, 3. The cardinality of set C is equal to 3. As you can see, A is equal to B is equal to C. All of these sets are equal to each other. What is our conclusion? Note, we don't have repetition. We don't have repeating elements in a set. What is the second conclusion? We can rearrange the elements in a set. Rearrange the elements in a set. This is true for any set. Let's take a look at part B. Part B says, is it true? Are these two equal to each other? Is set including 0 is equal to 0 itself? Let us analyze this. What's going on here? What entity do we have on the left? What entity do we have on the right-hand side? On the left-hand side, we have a set including 0, including a member which is 0. So the entity on the left-hand side is a set. The entity on the right-hand side, however, is just a digit. It is a digit. Is a digit equal to a set? The answer is no. So set in general is not equal to a number or a digit. So in general, if you have a set on one side and a digit or a number on the other side, you quickly say, hey, they are not equal to each other. So the set, including a digit, on the right-hand side, you only have a digit. Two different entities. Part C of this example says, how many elements? What's the cardinality? Are in this set. The set including 1 and set of 1. Guys, this is different. This is different from a set including 1 and 1. This set has two objects. Set including 1 and set 1 has two different objects. One of them is just a digit, the other one is a set. One of them is a digit, which is 1, and the other one is a set including 1. So the cardinality of this set, let us call it set C, the cardinality of set C, or the other notation, the other symbol, absolute value of C is equal to 1, 2, two objects. This is a finite set with two elements. C is a finite set. Perfect. So part D says, for each non-negative integer n, suppose you have a set, so part B says, suppose a set is defined this way, u sub n is equal to n and minus n, and it gives you the following condition that n is non-negative integer, and it says what is u sub 0, what is u sub 1, and what is u sub 2. So take a look at this. It says u sub 0. It means that wherever we see n, we're going to substitute that with 0. This is equal to 0, comma, negative 0. Negative 0 is equal to 0. So 0, comma, 0. Remember that we don't have repetition in a set. So this is equal to a set with only one member. This set has only one member. So it's a finite set with cardinality equals to 1. How about u sub 1? It means that wherever you see n, you're going to substitute that with 1. 1 and negative 1. This set has two members. It is finite with cardinality equal to 2. How about u sub 2? Wherever I see n, I'm going to substitute that with 2. 2 and minus 2. So this set has only two members. It's finite with cardinality equals to 2. Okay, just a quick review for you. The easiest set, the simplest set, is set of natural numbers. We denote it by n, and we say that, hey, n is the set of natural numbers or counting numbers. It starts from 1. 1, 2, 3, 4, and so on. Well, if somebody asks you to graph this set, you say, hey, I have 1, I have 2, I have 3, I have 4, I have 5, I have 6, and I have gaps in between these numbers. You cannot fill this gap. These are gaps. These are all gaps between these numbers. Of course, in math, we are interested in generalizing the idea. I expect you to ask, what about negative numbers? Where did 0 go? We can add 0, then we can add negative numbers. We use whole numbers to represent the set starting from 0. 0 union with counting numbers. 2, 3, 4, and so on. So let's continue this set. We have more members. Again, there are gaps in between these numbers. We cannot include fractions. We cannot include radicals. So you see gaps between these numbers. By adding negative numbers, we expand the system to z or integers, we have a lot of small negative integers. Let us list some of them. -3, -2, -1, 0, 1, 2, 3, and the rest of the counting numbers on the right-hand side. Again, we have gaps in between these numbers. We don't have fractions, we don't have radicals, none of them. I expect you to ask, how can I include fractions? We have to expand the system and define a new set that we call rationals. Q. Rationals is the set of all fractions A over B such that. Now that we know how to read a set, we have Q, rational numbers, the set of all fractions such that A and B, both of them are integers. A and B, they both belong to Z, integers, and the denominator is never 0. This set, rational numbers. Okay, we can fill in some of the gaps between these numbers using rationals. Now I expect you to ask, what about pi? What about square root of 3? What about e? How about those numbers? Those are non-rational numbers. Those are irrational numbers. So Q complement QC, Q complement includes irrationals like pi, square root of 3, e, and the rest of them. If you take the union of rationals and irrationals, you define real line. That's how we fill the gap. That's how we define the real line. By taking the union of rationals and irrationals, we have R or real numbers. So if somebody says, hey, graph real number system, you're going to use a connected line. It's not like this line with gaps in it. There is no gap. You filled all of those gaps using rationals and irrationals. This is R, usually denoted by Q, union QC equals to R. Every member on real non or x-axis belongs to R. Very well. So you all learned about intervals in algebra, in pre-calculus. Just be careful when you're reading the sets. For example, question says, graph these sets. The first set is the set of all numbers such that those numbers are real numbers with the condition that x is bounded between -2, and 5. The second one says, hey, now you have the set of all integers, such that x is bounded between -2 and 5. And C says, hey, let us work with positive integers with the condition that those positive integers are in between -2 and 5. Okay. So we know that there is no gap for real numbers. To graph this, we use real line. We find -2, we find 5. Since -2 and 5 are not included, we just use open circles to exclude the boundaries, and we shade the rest of the numbers in between them. It means that there is no gap in between, and all numbers are included between -2 and 5. But what if I change the domain to Z, just counting numbers? So if I list the numbers here, it's going to be -1, 0, 1, 2, 3, and 4. It means that if I want to graph this, I cannot shade all the numbers between -2 and 5. I just need to use some circles specifying these numbers. -1, 0, 1, 2, 3, and 4. There are gaps in between these numbers. And finally, if it has a plus sign on top of it, it's equivalent to saying that you are working with n natural numbers. Well, here we go. Natural numbers start from 1. So it's going to be 1, 2, 3, and it stops at 4. 1, 2, 3, 4. So we have 1, we have 2, 3, and 4. Well, now I expect you to ask, okay, you define some new objects, sets. How do I create a new object using this new object? So this is the question that you want to answer. How to create a new object using sets. Suppose you have a set and you want to create a new object. In this case, we can define a subset or subcollection of a set. Definition of a subset. Let S be a set, a subset of S is any subcollection of elements of S. So suppose A is a set. Let us work with B to follow the note. Suppose B is a set, a subcollection of B, or a subset of B is another set. Like A. We denote it this way. We say A is a subset of B. So set A is a subset or sub-collection of set. We can use Venn diagram to represent it this way. This is your bigger set, set B. And this is the smaller set. There's a possibility of these two sets be equal to each other. Set So what's the official definition? We say that B is a set, a sub-collection of B is another set A. Officially, we say that set A is a subset of B if any element in A, if X is in A, it is in B. Set A is a subset of set B. If I take any random element in set A, that random element belongs to the bigger set B. When visualizing a subset and a bigger set, it's easy to see that if we take any random element in the smaller set, that element for sure belongs to the bigger set. So if we take a random element like X in the smaller set, it is in the bigger set. That element belongs to the bigger set. If we are sure that A and B are not equal to each other, then we write A as a subset of B, and we say that A is a proper subset of B. A is a proper subset of B. For example, you can say that, hey, natural numbers is a proper subset of whole numbers. Natural numbers is a proper subset of integers. Natural numbers is a proper subset of real numbers, and so on. Because you're sure that there are gaps in between natural numbers and those gaps cannot be filled. So definitely, natural numbers is not equal to real numbers. Okay, give us some examples. Two examples for you. Let A be positive integers. And suppose B is the set of all integers, so n belongs to Z, such that n is sandwiched between 0 and 100. And suppose C is given as the set including 100, 200, 400, 300, and 500. So which one is true? Which one is false? A says B is a subset of A. B says C is a proper subset of A. C. It says C and B have at least one element in common. It means that the intersection between B and C is not empty. And D says, well, C is a subset of B. And E says C is a subset of itself. Okay. Is B a subset of A? Okay, it means that if I take any random element in set B, that random element must be in set C. So set B includes 0, 1, 2, 3, and so on. And for example, 0 is not a member of, let me see. Oh, this is B and A. Okay. So here, take 0. If we take 0 in B, 0 is not in A. Because we say that, okay, Z with a positive sign on top of it is the same as n, natural numbers. And natural numbers start from 1. So, of course, B is not a subset of A. So this is false. What about B? Is C a proper subset of A? So take a look at the elements in C. 100, 200, 300, 400, and 500. And A includes all positive integers or just natural numbers. There is no way C is equal to A. It's just a subset. So this is true. So what about this case? Do you see an intersection between C and B? C and B, of course. 100 is in the intersection between C and B. 100 is in the intersection of C and B. There is at least one element in common between them. True. What about B? C is a subset of B. Well, C is a subset of B. It means that if I take any random element in C, that random element must be in B. If I take 100, yes, 100 is in B, but you have the choice of selecting 200. If I select 200, 200 is not a member of B. You might say, hey, I'm going to randomly select 400. Yes, 400 is in C, but not in B. So this is false. Since 200, or you can say 300, 400, 500 is in C, but not in B, C cannot be a subset of. And finally, C is a subset of C. This is always true. Any set is a subset of itself. Any set is a subset of itself. It's always true. And And the last example that we have here, which one is true? Which one is false? Okay. This example says part A, 2 belongs to set 1, 2, 3. B, set 2 belongs to the set including 1, 2, 3. C, 2 is a subset of set 1, 2, 3. D, set including a digit is a subset of set including 1, 2, 3. E, set including 2 is a subset of set including 1 and 2. And F says set including 2 belongs to the set including 1, including 2. Well, which one is true? Which one is false? Well, 2 is a member of this set. You can actually see this here. Set including 2 is not. This is a new object. Is not a member of this set. Take a look at this. I want to compare B and F for you. Set including 2 is a member of the set including a set of 2. This is true. 2 is a subset, so you have to stop here. 2 is not a set. This saying that, hey, you have a digit, a number as a subset, there are 2 different entities. You cannot compare them. This is false. What about this case? You have a set including 2 as a subset of this set. Take random element. You can see this random element belongs to the bigger set. This is true. This says a set including 2 is a subset of this set. Okay. Here you have random element 2. Is this random element a member of this set? Unfortunately, not. So for this, you can say that we cannot compare a digit to a set. And for this one, you can say that this set is a subset of a set if it was like this, without having the set notation.